Ever since Algebra 1, we use this formula for a slope, which is the slope is equal to y2 minus y1 over x2 minus x1. And this idea that this would be the slope worked because when we had a line, with this being the x-axis and this being the y-axis, we would choose any 2 points on the graph, this being x1, comma y1, and this being x2, comma y2. We would use this to find the slope. Now this works for lines because their slope is consistent throughout the entire function. Now what if we had something like this, a curve? Well, if we were to pick 2 points on the graph and then draw a line, this line, as you can see, there is a little part sticking out. So this wouldn't work for curved lines. So how could we get the slope of a curved function if the function slope does not stay consistent and always changes? Well, what if we had just 1 point and we made a line only touching that point? We would get a slope for that special point. Now, how do we get that? Only using one value, because that point would be x, comma, y. Now, what values are we going to use this slope formula? Let's go ahead and make our original line again, touching 2 dots. This is called a secant line, where it touches 2 points on the graph. We will represent that with green. This, however, I'm representing with red on that dot, is a tangent line, which only touches 1 point on the graph. Before we list these points, let's go ahead and state that f of x is equal to y. If you don't know what f of x just means a function is equal to this x output. So whatever this x output, for example, if we had a function f of 2 and we had x squared plus 4, something like that, that would just mean plug in the x value as 2. But for now, all you need to know is that f of x is equal to y. So what would we call these points? Well, this green point is going to be named x, comma, f of x. It's just f, comma, y. Think of it like that. Now, what is this point going to be? Actually, what we're going to label here is x plus h, comma, f of x plus h. Now, let's wrap our heads around that really quick. So, why did I choose x plus h and not x2? Well, let's think of h as a distance. What I'm essentially doing is I'm taking this x point and adding some type of distance such that from this point to here is h. So if I start at x to get to x plus h, I add h and we get our distance. So now that we have our x plus h, how did I get f of x plus h? To get our f of x plus h, if you remember what I said over here, f of 2 to a random function, what we have to do is just plug in 2 to get our output. Now we have f of x plus h. So that means that function that we had is going to be f of x plus h, and every unknown value is going to be x plus h. If this helps, think of h as a random distance. Let's do x plus 3. That means if this distance was 3, that means we'd have to go over 3 to get to x plus h. So if x was 2 and we went over h, we would be at 5. But we're using variables, so we can apply this to any situation when we get to the definition. So now that we have our points, let's list them here. So our first point is x comma f of x, which is x comma y. And our second point is x plus h comma f of x plus h. Now we have the setup to use our slope formula. So we have our y1, our x1, our x2, and our y2. So let's go ahead and put it together. Slope is equal to f of x plus h minus our y1, f of x, over x plus h minus x. And as you can see, down here we have x minus x. So these x's cancel out. So our slope is now equal to f of x plus h minus f of x all over h. Now wait, there's a problem here. This is how you get this line. How can we get it such that it only reaches one point? Well, let's think. If h didn't have a distance, we would essentially be on the point. Think of it like this. If this point in blue were to travel along this line to that point, we would essentially have no distance between our x and our x plus h, because our x plus h wouldn't have an added distance. So how can we get h to have no distance? Well, in order to do that, we need to take the limit as h approaches 0. Basically what that's saying is if we have h go all the way to 0, we will essentially be back all the way at that point right there, essentially closing the distance and having this secant line go all the way and turn into a tangent line. In case you need it, here's a more visual approach to the derivative. So here is the secant line I was talking about, where it touches 2 points on a graph. Now, what I was trying to get across was if you had a distant h, if that point goes closer and closer and closer, where our h value is basically 0, we will get a tangent line. So if we have the limit as h approaches 0 of f of x plus h minus f of x all over h, that is equal to our derivative. Now, you can take this concept and apply it to any 2 points on a curved graph to find the slope at a particular point. Later on through calculus, this concept becomes more simplified to the point where there are different rules you can use in order to make the process easier. Now you know what the definition of a derivative is.